Okay. Today is a review for exam 1. The time of the exam is this Thursday. Normal time is the class meeting, 11 a.m. to 12:15 p.m. The location is classroom building, 105. The sections covered by this exam is section 1, section 2, section 3, section 4, section 5 in chapter 1. 5 sections. This exam is close to the notes and close to the book. But you can have a formula sheet, A4 size. You can write anything you think is helpful for the exam on the both sides of the formula sheet. And also you can have a basic scientific calculator. Suppose your calculator cannot compute, say, a matrix times a vector, right? Very basic. How to prepare for the exam? I suggest review your homework. I post the homework solutions on Wild Course. You can find them on Wild Course. Second, read some examples in the book. And also try some problems in the exercise sections in the book. This is my suggestions to prepare for the exam. Okay. Now, today, I want to pick some problems to present, the problems from exercise sections in the book. Section 1. What is section 1 about? It is about elementary row operations. By using elementary row operations, we can simplify a matrix by introduce zeros to the matrix. 3 elementary operations. Number 1, you can interchange 2 rows. Right? Row I, row J. Switch them. Number B. You can scale 1 row, scaling. The notation is some number times some row. Then we have a new row. Put the new row in row I. Okay. It is important. C, non-zero. Okay. Operation C is the name is replacement. The operation is some number times some row, say row J, and then plus row I. Here this number can be 0, can be non-zero. It doesn't matter. Now we have a new row. Then put the new row, not in row J, but in row I. Yeah, this operation is called replacement. These 3 operations, they don't change the solution set of a linear system. Keep the solution set, but we can simplify the linear system. This is what section 1 is about, elementary row operations. Now, section 2. It is about epsilon form. Epsilon form. Epsilon form. When we solve a linear system, reduce the linear system to epsilon form. But epsilon form is not the simplest form. We can continue to introduce zeros to epsilon form. The most simple form is reduce epsilon form. Reduce epsilon form. The precise definition, okay? Definition. You can find the definition of epsilon form and reduce epsilon form in the book. Which page? Let me see. On page 37. 37. Okay. Yeah. Still, let me present the definition here. Okay. What is epsilon form? Epsilon form. If a matrix has the following 3 properties, the matrix is called in epsilon form. Property number 1. All long zero rows are above 0 rows. Property 1. Property B. Second property. The leading entry of a row. Leading entry, that means that from the left to the right, the first non-zero entry is called the leading entry. The leading entry is in a column to the right of the leading entry of the row above it. Property C. All entries in a row, in a column, below a leading entry of the row, below a leading, all entries in the column below a leading entry are zeros. If a matrix has these 3 properties, then the matrix is called in epsilon form. I will show you examples. Epsilon form, not the simplest. We can still introduce zeros to epsilon form. Furthermore, okay. Further, if a matrix in epsilon form satisfies the following two additional conditions, then the matrix is called in reduced epsilon form. Okay. A. The leading entries, the leading entry in each row is 1. That means you need to scale each row so that the leading entry is 1. B. Each leading one is the only non-zero entry in its column. Yeah. These two are the definitions of epsilon form and reduced epsilon form. Now, let me pick one example from the book. Say, problem 1, section 1.1. Section 1.2. Example. Take a look at one example. Determine which matrices are in epsilon form and which are in reduced epsilon form. We have 4 matrices here. Number 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. Second matrix, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. The third matrix is 1, 0, 0, 0, 0, 1, 1, 0. Zero, 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 zero. And the fourth matrix is 1, 1, 0, 1, 1. 0, 2, 0, 2, 2. 0, 0, 0, 3, 3. 0, 0, 0, 0, 4. Yeah. 4 matrices. Which ones are in epsilon form and which are in reduced epsilon form? Okay, now take a look. The first matrix. It is in step-like pattern. It is easy to verify that this matrix satisfies all these 3 conditions. So the matrix is in epsilon form. Epsilon form. Yeah. And also this matrix also in epsilon form. And in epsilon form. in epsilon form. How about this one? Yeah, I think so. In epsilon form, satisfy all the three properties in the definition. Now, all matrices are in epsilon form. Okay, all are in epsilon form. Okay, now which ones are in reduced epsilon form? I think the first one in reduced epsilon form. Yeah, reduced epsilon form. The first one. Yeah, leading all the leading entries are 1, and the leading entry is the only non-zero entry in its column. Yeah, this matrix is in reduced epsilon form. How about the second matrix? I don't think so, because you see, we still have some room to introduce zeros to the matrix, right? If I let -1 times the second row and add to the first row, then this one is gone. So this is not in reduced epsilon form, not simple enough. How about this one? Yes, this is in reduced epsilon form. We cannot further introduce any more zeros into the matrix. Epsilon form. The last matrix clearly not in reduced epsilon form, because leading entries, they are not 1. So the last matrix is not in reduced epsilon form. Yeah. So this is about the definitions of epsilon form and reduced epsilon form. This is a section 2. Next, section 1, section 2, and section 5. They are all about solving linear systems. Okay. Solve linear systems. Here is a summary about solve a linear system, a general linear system. Okay, a summary. A summary. How to solve a linear system? Okay. Yeah, this is a linear system in matrix form. Okay. Step 1. Perform forward elimination by the 3 elementary row operations. Forward elimination to simplify the linear system into epsilon form. To reduce the augmented matrix, coefficient matrix, together with the right side, augmented matrix, to epsilon form. Epsilon form. Now, after this step is finished, then we can determine whether the linear system has a solution. Okay. 2 cases. Case 1, if the bottom non-zero row, non-zero, when a row contains 1 non-zero entry, then the row is non-zero row. If the bottom non-zero is in this form, 0, 0, 0, then the right hand side non-zero. Yeah, usually this notation means non-zero number. Okay, yeah, non-zero number. Okay, then the linear system, the system has no solution. In other words, the linear system is inconsistent. Any example? Say, yeah, this is one example. 2, 1, 0, -1. 0, 3, -3, 0. 0, 0, 0, 4. 0, 0, 0, 0. Yeah. The bottom non-zero is row 3. But row 3 is in this form, right? 0, 0, 0. Then right hand side non-zero. Then this linear system has no solution. No solution. Second case. Otherwise, if the bottom non-zero is not in this form, otherwise, the system has at least one solution, has a solution. Say, for example, how about in row 3, how about let me switch this number 4 and this 0. Yeah. 2, 1, 0, -1. 0, -3. 0, 0, 0, 4. Let me switch. 0, 0, 0, 0. Yeah. This linear system has solutions. Okay. Look at the bottom non-zero. Yeah. Row 3, non-zero. But row 3 is not in this form, right? So the linear system has a solution. Row 3, actually, if you write row 3 in equation, then row 3 is this equation. 4 times x3 is 0. This equation has solution. What the solution is? The solution is x3 is 0. This linear system has a solution. x3 is 0. How to determine x2? Plug x3 in the second equation. Then we can get x2. Plug x2 in the first equation. x3 in the first equation, we can get x1. So this linear system has a solution. Okay. Now, step 1, perform forward elimination to reduce the augmented matrix to epsilon form. If the linear system has solution, then step 2. Step 2, B. Suppose the system has a solution. Has a solution. Then how to find all the solutions? Perform backward elimination to further simplify the linear system. Perform to reduce the epsilon form in step 1 to reduce epsilon form. Now, also there are two cases. Case one, if after you obtain the reduced epsilon form, then determine which unknowns are basic, which are free. If low free unknowns or variables, then the system has a unique solution, only one solution, exactly only one solution. Any example, say for example, 1, 0, negative 1, 0, 1, 1, 0, 0, 0. No, this is still not in reduced epsilon form. Let me replace this one by 0. Replace this one by 0. Yeah. Say 1, 4, for example. Yeah. This linear system has low free variable. The first column contains a pivot. So X1 basic. Second column contains a pivot. X2 basic. Third column also basic. Okay. All are basic. So this linear system has only one solution. On the other hand, if there is one or more free variables, then the system has infinitely many solutions. Yeah, this is a summary about solving a linear system. Now, let me show you one example. Yeah, one example. Example 1. Okay, so the following linear system. 0, free. The linear system is given by augmented matrix. 7, negative 9, 6, 8, 12. Four, a coefficient matrix. Then the right side is negative 5, 9, 15. All right. Solve the linear system. Then write its general solution in vector form. Okay. Two questions. One is solve the linear system. After you get the solution, then write the solution in vector form. Okay, now solution. Perform forward elimination. Okay. Because I cannot use 0 to eliminate non-zero numbers. So the first step is switch row 1 and row 2. Here, in my logs, I switch row 1 and row 3. Then I get 3, 9, 12, 9, 6, 15. As 0, 3. Okay. Now I can use this number. to eliminate the number 3 below it. Okay. We call this number pivot entry, pivot number, and correspondingly the location, 1-1 location, the 1-1 position is a pivot position. So in the original matrix, yeah, this position, not this number, this position is a pivot position. The first column is a pivot column because the first column contains a pivot position, and also first column corresponds to the unknown x1. So x1, we call it is a basic variable. Okay, now I use this number to eliminate this number. So -1 times first row plus row 2. Put the result in row 2. Don't put the result in row 1. Then again, this matrix 12, 9, 6, 15, 0, 2, 4, 4, 2, -6. Separate, yeah, separate. Okay, now continue the forward elimination. Now this time, I use this number to eliminate the number 3. Okay, this number is a pivot number or pivot entry. And the 2-2 location is a pivot position. Second column contains a pivot position, so the second column is a pivot column. Pivot column. And also variable x2, right? Second column contains the coefficients of the unknown x2. So x2 is basic. Basic. Okay. Now I multiply row 2 by -3/2, and then add the result to row 3. Then this number 3 is gone. -3/2 times row 2 plus row 3. Put the result in row 3. Then we have this matrix. Zero, 2. And 0, 0, 0, 0, 1, 4. Now this matrix is in epsilon form. So forward elimination is done. About this entry, we still consider this entry a pivot entry. Yeah, a pivot entry. Why this entry is still considered a pivot entry? If they were numbers below it, we would use it to do elimination. And also we use it to create zeros above. So this is still a pivot entry. The location is 3, 1, 2, 3, 4, 5. 3, 5 position is a pivot position. Therefore, column 5, the 5th column is a pivot column. And the variable x5 is basic. A basic variable corresponds to a pivot column. Okay. I'm done. Okay. With forward elimination. Then take a look at the bottom non-zero row. Yeah, bottom non-zero row. This row is not in this form. 0, 0, 0, 0, 0. Then non-zero, not in this form. So therefore, the linear system has at least one solution. How to find the solution? Backward elimination this time. Continue to simplify the matrix. Now, backward elimination. To reduce the epsilon form to the reduced epsilon form. I continue to introduce zeros to the matrix. Backward elimination starts with the rightmost pivot entry. Okay. Now I use this number 1 to create zeros above. To eliminate 2, I net -2 times row 3, then plus row 2. Put the result in row 2. And also I use this number 1 to eliminate the number 6. -6 times row 3 plus row 1. Put the result in row 1. So then the matrix is 3, 9, 12, 9, -9, 0, 2, 4, 0, -14, 14, 0, 0, 0, 0, 1, 4. Then put a 9, separate the coefficient matrix and the right side. Next, I use this number, the leading entry in row 2. I use this number to eliminate -5. So this number is a pivot number, pivot entry. And again, the 2, 2 position is a pivot position, column 2 pivot. Okay. Okay. +9/2 times row 2, then add to row 1. I get this matrix. Uh, 72. Actually, it's wiser to scale row 2 first, right? Divide the row 2 by the number 2 first. Make your computation easier. 0, -2, 4, 4, 0, negative 14, and then 0, 0, 0, 0, 1, 4. Yeah. Okay, the final step, scale the leading entries. 1, negative 1 over 2 times row 2, scale row 2, put the result in row 2. And also scale row 1, 1/3 times row 1, put the result in row 1. Then we have reduced epsilon form. (24) a 1, 4. Hey, now the next step is write the final augmented matrix in equations. In equations, the final augmented matrix is the first row. First column are the coefficients for the unknown x1. So x1 0 times x2 minus 2 times x3 plus 3 x4 0 times x5 is equal to right hand side. First equation. Now the second equation corresponds to the second row. 0 times x1 and then 1 times x2 minus 2 x3 plus 2 x4 is negative 7. Now the third equation is x5 is 4. For the general solution, solve this linear system for the basic variables in terms of the free variables to get general solution. Okay. Now, in the first equation, I move the free variable x3, x4 to the right side. In the second equation, I move x3, x4 to the right side. Then the general solution is the general solution is x1 is negative 24 plus 2 x3 minus 3 x4. X2 is this. X5 is a constant, right? Always 4. Okay. Here x3, x4 arbitrary 3. Yeah. This is the general solution. I'm done with the first question in this example. Yeah. Solve this linear system. I'm done. Okay. Now, second question. Write the general solution in vector form. In vector form, the unknown, I put all the unknowns into a vector. x1, x2, x3, x4, x5. Now, plug in the first equation in x1. Second equation in x2. Third equation in x5. Okay, but here x3, keep x3. it is a free variable. Also keep x4. And then x5 is 4. Yeah, it's 4. Now split this vector into a sum. The first vector contains constants, negative 24, 7. The third entry, the constant is 0. 0. The fifth entry, the constant is 4. Yeah. Then plus second vector. Let me see. We have two free variables, x3 and x4. Now the second column is for x3. So 2x3, 2x3, x3. Now the fourth entry has low x3, so put a 0 here. The fifth entry, low x3, put 0. Yeah. Now the third column is for the unknown, x4. 0, x4, then 0. Now finally, take out the variable. Take out x3. 2, 2, 1, 0, 0. And then take out x4. 1, 0. 1, 0 here. 0 here. Okay. Yeah. 1, 0 here. Yeah. So this is the answer to the second question. Write general solution in vector form. Because from the beginning to the end, in linear algebra, we need to solve linear systems. So you should know how to solve a linear system. In exam 1, I can guarantee there must be a problem similar to this example. Okay, solve a general linear system and then write the general solution in vector form. There must be one problem very similar to this example. Next, let me continue to pick problems from the exercise section. Let me see.
I have a question real quick.
Yes.
So going back to when we were scaling to get reduced echelon form.
Yeah.
In the second row, second
row here, right?
1/2. Would it be?
You're talking about this row?
Yeah.
Okay.
So would it be 1, 2, -2, and 7? Just because you divide by -1/2?
Oh, correct. Sorry. Divide this row by -2. So this is a 1. Yeah. This should be +2. And this should be -2. Yeah, thank you. And also here should be +7. Correct.
Right,
thank you. Thank you for correct my mistake. Let me see. Let me pick. Example 2. It is problem 37 in section 1.1. In section 1.1. Okay. Suppose the following linear system is consistent, has solution for all f and g. Okay, for all f and g. What you can say about a C and D. The linear system is x1 plus 5x2. Then right side is f. C x1, D x2, right side G. Okay, yeah. This linear system has a solution for arbitrary right hand side. Then what you can say about C and D? Solve the linear system. Okay, yeah. Augmented matrix. Okay, now forward elimination. Negative C times first row, add to row 2. Zero, D minus 5C, G minus CF, right? The linear system has solution for arbitrary F and G. Yeah, this guy arbitrary. The linear system still has solution. What it means? It means that this number cannot be 0. If this number is 0, then for some F and G, the linear system has no solution. So the answer, conclusion is conclusion. Okay. D minus 5C cannot be 0. That is the answer. Okay. This is example 2. Example 3, section 1.2, problem 36. Let me see. 1.2, problem 36. Here. Yeah. Example 3, problem 36, section 1.2. Suppose a system of suppose a system has a 3x5 augmented matrix. Whose fifth column is a pivot column. That means that after you reduce the augmented matrix, then you will see the fifth column contains a pivot number. Okay, now the question is the system consistent? I don't know. Solve the linear system. Okay, yeah, the linear system. Solve the linear system. How? Augmented matrix. Now perform forward elimination. Let me skip because I don't know the matrix. I don't know a B. So I cannot tell you the detail about the row operations. So I use tutor to skip the detail. Now, after I reduce this augmented matrix to epsilon form, then epsilon form. I don't know. There are many possibilities. Say, suppose here, non-zero. A star means 0 or non-zero. the size of the augmented matrix is 3 by 5. So, okay. Star, then star, 5, right? 5 entries, yes. And then 0. Star. Okay, now the last column is a pivot column. What it means? Last column contains pivot entry. Pivot entry is leading non-zero entry in a row. So the third row should be in this form. Right? Do you agree? Yeah. Of course, this matrix has other possible epsilon form, but here this is only one possible epsilon form. Okay, the fifth column is a pivot column now. Then this matrix, this linear system has solution or not? No solution, because the bottom non-zero row is in 0, 0, 0, 0, non-zero, this form. If you write this row in equation, you will get 0 times x1, 0 times x2, 0 times x4, 3, 0 times x4 is non-zero, impossible, no matter what values for x1, x2, x3, x4. You cannot make this equation true. Linear system has no solution. Yeah. The answer, okay, to this question is inconsistent. Okay, inconsistent, no solution. This is example 3. Example 4. Let me see. Let me pick. Example 4. Okay. Actually, this is a homework problem. Okay, suppose under determine system happens to be consistent. Undetermined system means the number of equations less than the number of the unknowns. Explain. Why they must be an infinite number of solutions. Okay. I don't know the system, the size. I don't know the size of this system. Say, suppose say 3 by 5. Suppose, okay, suppose 3 by 5. Augmented matrix. Augmented matrix. An undetermined system can be inconsistent, can be consistent. Say, for example, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, say 1. Yeah. This linear system has 3 equations, 4 unknowns, undetermined linear system. But this linear system has no solution because look at the bottom non-zero. The bottom non-zero row means 0 is equal to 1, impossible. So undetermined linear system can have no solution. Okay, now suppose a determined system happens to have solution. Why? There are infinitely many solutions because the linear system has 3 variables. Okay, say take a look at this. 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, then 0, 0, 0, 0. Yeah. This undetermined system has solution because the bottom non-zero not in this one. But the number of equation is 3. Unknown is 4. There must be at least 1 free variable. In this example, x2 and x3, they are free. When a linear system has a free variable, there are infinitely many solutions. This is an example 4. Example 5. Section 1.3. Number. Oh, good. Example 5, right? Example 5. Problem 22. Section 1.3. Right. Construct a 3 by 3 matrix A with non-zero entries. All the entries are non-zero. And construct a vector B. It is in R3. The vector has 3 entries. Such that vector B is not in the set span by the columns of the matrix A, by the columns of matrix A. Right? So here, you need to review what it means. A set spanned by vectors. Each column of a matrix is a vector spanned by the columns. All right, now let me try. Okay, low entry is 0. Okay, let me try. Make my construction as simple as possible. Okay, say, let me try. Non-zero. So 1, 1, 1. First column. Second column. 1, 1, 1. 1, 1, 1. So all the columns, the same. So these 3 columns, these 3 vectors, because they're the same vector, if you plot the graph in R3. Say, suppose this vector is 1, 1, 1. Okay, all the 3 vectors, the same vector. So one vector can span only 1 line. Yeah, only this line. Now, what I need to do is construct a B, not on this line. That's it. About B, no requirement about its entries. B, the entries can have 0. So this is A. B, I don't think this vector is on this line. I don't think this vector is on this line. Why? Why B is not on this line? Solve this equation. Yeah. This equation, recall that a matrix times a vector, it is X1. Let me name the first column, second column by A1, A2, A3. A matrix times a vector is X1 times first column, X2 times second column, X3 third column is B. A matrix equation is a vector equation. Okay. Yeah, this vector equation has no solution. If the vector equation has a solution, then B is on this line. B spanned by the three vectors A1, A2, A3. Now solve this. Yeah, solve this vector equation. Actually, it is a linear system. This linear system. This linear system. Now solve it. Augmented matrix. 1, 1, 1, 1. 1. 1, 1, 1, 0. 1, 1, 1, 0. Yeah, solve it. How to solve it? Forward elimination. Then you will see no solution, right? -1 times first row, add to the second row. Okay. 0, 0, 0, -1. From here, I can tell the linear system has no solution because the second row is 0 is equal to -1. Impossible. -1 times first row to the third row. -1. Yeah. So this linear system has no solution. Therefore, B is not in the span of the columns of this matrix. Yeah. Example 5. Example 6. Let me pick. Okay. Example 6. Section 1.4. Problem number 3. Section 1.4. Section 1.4. One of the topics in this section is a matrix times a vector. There are two formulas. Okay. There were two formulas. Okay. Take a review. Okay. Take a review. Okay. Two formulas to compute A times a vector. V. V means vector. Okay. The first formula is you need to cut matrix A into columns. First column, second column. Suppose n column. We should have n entries. Otherwise, A times a vector not computable. So V1, V2, then Vn. Yeah. Now the formula is V1 is number times first column, and V2 times column 2, and so on. Vn times column n. In other words, a matrix times a vector is a vector. That vector is a linear combination of the columns of the matrix A. Okay. Formula 1. Formula 2. A times a vector. It is a vector. The I entry I. The formula is row I of A times vector V. Yeah, write down these two formulas on your formula 3. Okay. What is row 1? AI1, AI2, and AIN. Row I of matrix A times vector V. Vector V is a V1, V2, and Vn. Okay. Now, next, the meaning of row I times a vector means the sum of the products of the corresponding entries. So it is a AI1 times V1 plus AI2 times V2, and so on. AIN times Vn. Yeah, two formulas to compute a matrix times a vector. Okay. Now, problem 3. Okay, now problem 3. Simple. Compute. Problem 3. Compute this matrix 6, 5, 3x2 matrix times 2-dimensional vector. Okay, 1, 3. You can use either of these two formulas to solve the problem. Say, let me use formula B. Okay, formula B. Okay, it is a vector. The product is a vector. It's a 3-dimensional vector. Okay, the first entry is row 1 times the vector. So 6 times 1 plus 5 times -3. The second entry is row 2 times the vector -4 times 1 plus -3 times -3. The third entry is row 3 times the vector 7 times 1 plus 6 times 3. So the answer is -9, +9, then 5, -11. Yeah, that is the answer. Done. So I don't have time to present the other problems. Yeah, I prepare many problems, but I don't have time to present them. Okay, let me stop here.